What up, what up? Alright, let's do linked lists. So, obligatory, summer moves fast. Let's get right into it. So, we want to learn about linked lists today and start on programming test 3. And with programming test 3, there is a pretty good spike up in difficulty going from tests 1 and 2 to 3, and also another spike up going to programming test 4, and then in my opinion it levels off after that. But I just want to give you a heads up on that just in case you're getting complicit doing test 1 and 2. You're like, oh, test 1 and 2 were pretty easy, I got this. First of all, you got it. You got this. You're gonna do well as long as you keep at it in this course. But do expect test 3 to take a bit more time than tests 1 and 2 did. Oops, I gave it a poop emoji. Why is that even a feature? What? Test 3 is not poopy. So some of you will think it is by the end of it. But test 3, I just want to do quickly. Let's remove ratings by reviewer. This is where I expect you to spend most of your time on the assignment. So getting through, if you're going through test 3 and you're like, oh, Jesse said there'd be a big jump up, and you get through the first 3 methods here and you're blowing through it pretty quick, just know that remove ratings by reviewer is going to be the bulk of the difficulty of the assignment, including testing remove ratings by reviewer. And the helper method and the average rating method and testing average rating, those will take a little bit of time, but that's more of a warm-up to the big thing that is remove ratings by reviewer. So don't be surprised if you're spending more than half your time on the assignment on just this one method plus its testing. And with testing, just something I've seen a bit on test 2 already, and I see it every semester, but just to say this, hopefully this helps at least one of you out there, is please use, I mean, it's not please, like I'm not pleading, but for your own good, use the testing utility methods. The way the assignments are structured is you write a testing utility method, and then you write your testing that will use that testing utility method. So when we have this compared list of ratings, actually let me jump to something that y'all are familiar with already, test 2. When you write your compare songs method, compare ratings is actually the one that trips everyone up, so let me use this one. When you write your compare ratings method, the idea is that in your testing, when you're testing these classes, you're creating a new ratings object with the values that you expect, and then calling compare ratings with that object and also the object that was returned from the method that you're testing. So when you're testing the reviewers rate song method, and that returns a rating object, you get that rating object, that's the one you're testing, and then you create a ratings object with exactly the values that you expect, and then you call compare ratings to actually do the comparison of those two objects. That's the intent of all these testing utility methods, is that we write these methods, Autolab checks them for you to make sure that they are doing what they're supposed to be doing, and then use them to make your tests easier to write. Because what happens, what a lot of the office hour questions and Piazza questions are students who aren't testing everything. So you test the rate song method from the reviewer, you check the rating of that review, but you neglect to check the reviewer ID. The object only has 2 instance variables, you have to check them both. And a lot of students will forget to check the other one. You can't make that mistake if you use the compare ratings method. You will never, without even thinking about it, you cannot make that mistake. You'll never forget. And that's part of the idea of these compare methods, these utility methods, is you can't make little mistakes like that. And you would avoid the Piazza questions, the office hour visits. You're going to save yourself time if you follow the structure of the assignment as intended. If you go against the structure of the assignment, things, you shouldn't be surprised that things are more difficult for you because you're going against the design of the assignment. If you're struggling to use the testing utility methods, that absolutely, I'd love to have that office hour visit where you're like, look, I know you want me to use these compare methods, but I just don't know. I don't know how to set that up. I'll be happy to guide you through. I'll love that office hour visit where I get to show you how to do something new. So test 3, when you have compare lists of ratings, This will take two linked lists of ratings and compare, make sure they have all the same values in the same order and that the lists are the same length. It'll do all those checks for you. So when you're testing remove rating by reviewer, which has to test a linked list, you'll create the linked list that you expect, call your method, which will be get ratings, and make sure get ratings returns that same linked list by calling compare list of ratings. Use the testing utility method. One of the biggest questions is, I'll bring this up multiple times throughout this lecture because it's the biggest thing that I see on test 3. One of the biggest things you're going to see is, especially on your remove ratings by reviewer tests, you're going to submit to Autolab, and Autolab is going to say null pointer exception. So if you see this, remember back, flash back to this moment, and remember this one thing: use your compare lists of ratings utility method when you're testing remove ratings by reviewer. If you do that, you will not see a null pointer exception, at least not a surprise one in Autolab, because what will happen is you'll run your tests on your code and everything's fine. You'll submit to Autolab and it'll say null pointer exception when your tests are ran against incorrect solutions. If you use compare list of ratings as intended, you'll never, ever, ever have that issue. If you use this method and you have that issue, make sure you come talk to me or email me or something. Get my attention and say, you were wrong. And then I'll look into it and see what exactly happened. Okay, so that's test 3. Very, very brief intro. Summer moves fast. I ain't got time to talk about it for too long. Let's do some code. So week 5, I've been calling this lecture, right? Lecture. And I want to go right to, I'm going to call this linked list node, but we'll get to that. First, I just want to write a main method with a few things in it. So we're going to learn about linked lists today, but I want to start by talking about array lists. Create a good old array list of integer. I'll call it numbers because whatever, new array list. I just want an array list. When I'm just going to talk about array lists, I don't really need the code, but without the slides, I kind of want it. And array list does have an underlying array, as we've seen last time. Just a reminder of that. But I want to talk about what an array is. Let's close all these, open this, condense this. It's fine. What an array list is. So let's say we do arrays.asList. And 7, 2, 9, 4. Sure. I don't know. We'll print to the screen. What an array list is, or what an underlying array is a continuous block of memory. So I want to talk about arrays to motivate why we even talk about linked lists. So let's talk about arrays, and this is actually going to show what I want, but not for the reason that I want. It's confusing, but I'm going to use it anyway. I'm going to use this example. So this, it's not right, but it gave me what I wanted anyway, so I'm going to use it. So what an array is one continuous block of memory. So when you get an array, and I'm talking about general arrays, I'm not talking about array lists specifically, I'm talking about the concept of an array across any language, is an array is a continuous block of memory for the values you want to store. So if I'm creating a plain array, it's a little different because this is an array list, but the concept would be I'm creating an array for 4 ints. I need to ask the operating system for enough space to store those 4 integers, and it will give me one block of memory where it's the first space for the first integer, space for the second, third, and fourth, all right next to each other in memory. And then we access those values by their indices, and we can see that the integers are right one after another in memory. The ats are right next to each other. That kind of was by coincidence that this happened, but in memory, they will be right next to each other. The reason is the integers are separate objects in different locations. It's kind of weird. So the debugger isn't exactly going to show what I want. But what's happening here is that, let's say this array is at index OX, we'll say it's at 500. Then array of 0 is at OX 500, OX 501, OX 502, OX 503. Assuming the array stores 32-bit ints. So the way an array, and then array of 1, I won't write the whole thing, but it starts at OX 504. So the way an array works is, if we ask for an array of size 4 that stores 4 ints, ints are 32-bit values, meaning that they are 4 bytes. And your memory, the way we have these memory addresses, your memory is one giant index, or one giant array of bytes. So each index, when we do these OX things, this is an index in that array, which is going to give us one specific location of one specific byte. And when we have a reference to an array, that's going to be a reference to the first byte of the first value in that array. So what would actually be stored in numbers would be just OX 500, and that array has OX 500 times 16, up to 16 indices after that, or 15 extra indices after that as well. So we only get a reference to the first byte though. And then using some math, we can figure out where all of our information is. First, we'll know that these are ints, so we know that it's 4 bytes per int. So the first int is at these 4 memory addresses. Then Java is going to take care of taking 4 bytes and combining them to one 32-bit int. It's going to do all that stuff for us. But under the hood, that int is stored across 4 different memory addresses, starting at OX 500. And if we want to get the value at any index, array of I starts at the starting index. We can do just a little bit of math to figure out where any value is at any index for this array. So we starts at the starting index, so the index of the first bit, the first byte of the first value, plus the size of each value. So since I have ints here, these are ints are 4 byte values. If this was an array list of doubles, morning, good afternoon. Wait, it's still morning here at least. Of course, I don't know where you're at. Good morning, good afternoon, good night, wherever you're at. If these were doubles, these would be 8 byte values, and this value would be 8 if we had doubles. We have ints, 32-bit values, so it's going to be 4 times I, the index we're looking for. So if we're looking for the value at index 0, this whole term zeroes out, and we just get the byte of the first value, which is, the starting byte is the first byte of the first value. If we want the value at index 1, this will be 1 times 4 will be 504, will be exactly where that next value starts, and we can get the value for any index I by doing one multiplication and one addition. So very fast operations. We can get to any value in the array. We can get the actual address in memory where that value lives very, very quickly. This is something called random access. We can randomly access any value in the entire array extremely quickly with almost zero extra work. One addition, one multiplication is like no work at all. And this is what they call random access. So the memory that we buy for our machines, we'll often refer to it as random access memory, or RAM. That's why we call it RAM, is because it is serving as one giant array with billions of indices of bytes that we can randomly access by given any memory address, which is an index in that giant array. We can get any value just immediately. Just give me that value immediately. This is also why we index at 0. It's so this math works out. Part of the reason is so this math works out. Plus a lot of other math just works out a lot cleaner if we index at 0, where index 0 just naturally gives us the first value. Index 1 gives us the next one. If we didn't index at 0, if we indexed at 1, we'd have to do something like I minus 1 here and have some gross stuff like that. And it's a third operator. It's not that big of a deal, but it can be, especially way back in the day when CPUs didn't process billions of operations per second. CPU time was a lot more precious. So cutting down one operation was a big deal. Especially if you have to code that in machine code or punch cards or something, you wouldn't want to do that. So that's part of why we index at 0. The math just works out a lot nicer for random access. The downside to this, so random access is a really nice feature. The downside to this is that an array cannot change size ever. We cannot change the size of an array. If I create this array with 4 values, I cannot, and remember, I'm talking about actual arrays here. You know what? Let me just code it up. Let me get rid of this. And we can actually make it as an int array. This is something I usually don't do in 116, whatever this course is. 116. I know what course it is. I'm joking. It's because it doesn't exist. Implicit toString on an array. Yeah, it doesn't like that. But we can do, that's part of why, I mean, working with arrays just isn't very nice. But we can do index. So this is allowed in Java. It's not something I'll show outside of this example in 116. But this array cannot change size. We cannot add a 5th element to this array. Because it's one continuous block of memory, we can't ask for these specific memory addresses. I'm not going to do the math real quick, but 5 whatever. We can't ask for those specific 4 memory addresses that we would need to be able to add a 5th value, because that's not how computers work. We can't ask the operating system for any specific location in memory. It is not allowed. That's not how we do things. We can ask the operating system for a specific amount of memory. We cannot ask it for any specific locations. If we could, things would be a bit more painful. If in your code you always had to worry about where you were asking for memory, it'd be a lot of extra code we'd have to write for every memory allocation. It'd be a bit of a pain, for one. But 2, it'd be very error prone, because if we ask, even if we can't ask for those specific memory locations, what if another program's already using those memory locations? Or more likely, what if our program is already using those memory locations? We can't just get those memory locations because they might not be available. And if they're not available, then what does our code do? Like, what do we do at that point? So we just can't do it. The operating system won't let us ask for specific values. So we can't change the size of this array. An array can never, ever, ever change size. The way an array list gets around this is with this grow method. We kind of saw this. I'm not going to go through the whole thing, but that's too much of a sidetrack for this. But what it's doing is creating a new array with double the size of, this code is unreadable at this level, but this is a bit shift operator to get actually that's a shift right, and shouldn't that be a shift left? Oh, old capacity. I'm not going to try to read this code live. This is pretty dense code. But what it's doing is creating a new array of double the size of the old array, and then copying all the values from the old array into the new array. So it's pretending that we can change the size of an array, but we actually can't. Array list is reallocating a brand new array somewhere else in memory, moving all the values to that new array, and then letting the old array get garbage collected. And that's why we like array lists. It's given us this illusion that we can change the size of an array because we like being able to change the size of our data structures. I like my ArrayList.add method, so I can just keep adding things to an array list. It's nice and convenient. But the actual array, if we worked with plain old arrays, like the string array we have right here, if we work with arrays, we cannot do that. You cannot change the size of an array. So we get random access, but we can't change the size of the array. And this is on the video, so you can always go back to it, but I'm going to delete all the array list stuff because we're going to go to linked list. Linked lists are a bit different, very different, in that they are spread all across memory. So your linked list is going to be all over memory, just scattered all around, which means we lose random access. We cannot just access any value of a node at will by index. We can't do that. But we can grow the size of a linked list. We can insert nodes, we can remove nodes, we can do whatever we want from a linked list in a linked list. So those are the two trade-offs we're going to get. We're going to trade away random access to get resizability, the ability to manipulate the lists as much as we want. And that's about all I'm going to say about trade-offs. When you get to CSE116, you're going to learn all kinds of data structures and talk all about the trade-offs between all of them. And that's what data structures are all about, is trade-offs. There is no singular best data structure. If there were, we would teach that one and only that one. But there's not. It's depending on your specific application, different data structures are going to be more appropriate. And by appropriate, I usually mean more efficient. It will be faster, more space efficient. And you want to pick the right one for your application to make your program as efficient as possible. So this is one of our first trade-offs between linked lists and array lists. You would use, depending on your specific application, what you need to do, you would choose one or the other. If you have data that's constantly changing size, you'd probably want a linked list. If you need random access, you would use an array list or an array. Okay, so with that, let's just talk about what a linked list is now. So a linked list is going to be based on objects on the heap and references to other objects on the heap, which is exactly why this content comes right after the classes and objects content, after we talk about constructors and references and objects and all that. Now we lead into linked list with that, very, very, very much by design. So a linked list is going to be, we're not going to create a linked list class, first of all, but we will create a linked list node. We're going to create linked list node objects, and those objects are going to know two things, which means they have two instance variables. They're going to have one instance variable, which is the value stored at that node, which is the value at that part of the list. And they're going to have a reference to the next, do not use, that was good for this reminder as well. When I'm using the autocomplete in lecture, and if you're using the autocomplete in your code, I allow it mostly because I have no way of knowing if you used it or not. The autocomplete, you can use it if and only if it types exactly what you were going to type, and you're just using it to cut down keystrokes. So I'm using it because I know I'm typing linked list node here. I accidentally clicked the wrong one. That isn't what I was going to type, and I have to notice that, delete it, and say that's not what I was typing. And I'm only using this to reduce my keystrokes. If that's what you're doing, that's fine. If you're using full line autocompletion, that is not fine. That is cheating. That's using AI assistance to write your code for you, where you start typing and it suggests an entire line. That's not okay. Absolutely not okay. But to the point where you can just hit enter, 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 and it'll write a whole method for you. If you have that turned on, that's cheating. Go to your settings. Go to settings. Search for full line. I forget exactly where it is. Inspections. I don't even have it installed on this one. So full line, but it'll say full line completion somewhere. I don't even have it enabled anywhere. Maybe it's a plugin. I forget. But if you have that, turn it off, lest you risk getting one of those emails from me that says you just failed the class for cheating. Okay. So linked list node. So we're also going to have a reference to a linked list node, because students do get in trouble with that all the time. They'll have code that has nothing to do with anything I've ever talked about in lecture, and then I'll be like, I know you didn't write that code. You had the tool write the code, the computer write the code for you. That that's cheating, right? And they'll post their cheating code right on Piazza. It's awkward every time. Don't do it. Don't do it. So, and it also has a reference to the next node in the list. So each node knows its value at that part of the list and where to find the next node in the list, which we'll call next. So those are the two things that a linked list node does. That knows. We'll have objects of type linked list node. They know the value at that location in the node and a reference to the next node in the list. So for now, we just need to know those two things, and we'll have a constructor that's going to create those. So I'm going to type linked list node. That's the first thing. I just don't feel like typing the rest of the characters, so I'm going to use autocomplete there. But the rest of this, it's not going to help me. So I'm going to have to type out the rest of these. And I'm going to be consistent with my slides just because it's there's something I want to talk about. I'm going to call this val instead of value. And I'll still have to call this one next because I don't know why. I just feel like in linked list node, I don't feel like typing out again. And then this dot value equals val. This dot next equals next. So we have a constructor that's just going to initialize our two instance variables. It doesn't do anything else. So not too fancy of a constructor. And that's our linked list node class, at least for now. We'll add to this throughout the lecture, but at least for now, this is our linked list node class. That's all we really need for this class. Now, there's going to be other things we'll add. For example, we have private instance variables with no getters and setters, so we're going to have to fix that later on down the road. But for now, let's just use this, and we'll write our testing code inside the linked list node class, so we will be allowed to access these instance variables directly. There's not going to be any harm in doing that. And then once we're outside of the linked list node class, we'll add our getters and setters. Okay, so let's create our first linked list. So we'll create a linked list node variable, which is going to store only the first node in the linked list, which sometimes we'll call head. The head of the linked list is the first node. We'll use head and tail sometimes. Head being the first node in that linked list. So first equals new linked list node, and we'll store the value, let's go 8. And then to indicate the end of a list, so when we're bouncing around, we'll bounce around memory here. We're going to store a reference to the first node in the list. We go to that object on the heap. It's going to know the first value of the linked list, and it's going to know where to find the next node in the linked list. We follow its next reference, go over somewhere else in memory. We don't know where, wherever the operating system gave us some memory. We're going to head over there. That node is going to know the second value in the linked list and a reference to the third node. We're going to use that reference to go to the third node. We're going to look at the third value. We're going to follow the reference somewhere else in memory to find the fourth node, get the fourth value, so on and so forth. That's how we're going to find our linked list. So we're constantly bouncing all over memory to get all of the values in this linked list. So my question is, how do we know when we're done? How do we know when we've reached the end of a linked list? And I'm going to answer that question right away. The way we're going to indicate the end of a linked list is by using the keyword null for the next reference. So instead of having next be a reference to another linked list node, we're going to have next store the keyword null. What null means is the value that's stored in this variable is supposed to be a reference. Whatever's here is supposed to be a reference, but there is no reference. Null means there is no reference here. And we can use null for any one of our class types. If we have a string, str, sure. We can have a string equal to null, for example. What this means is that, I don't like this example. We do a linked list node. It's no list. I don't want to show null strings because we treat strings as primitives in our memory diagrams. That's confusing seeing null as a string. But we can have our linked list node equal to null. What this means is noList, the variable, is supposed to store a reference to a linked list node object on the heap, but it doesn't. So this does not store any reference. It just stores what we call a null reference. There is no reference. The big thing to know about this, and the big thing most of y'all will see on your test 3, somewhere along the lines of test 3, writing the code, testing it, submitting to AutoLab, is a null pointer exception. So a linked list node list has, let's say, a value. Let's just say we want to print that value to the screen. System.out.println. I don't want to type it all, so I just do s out. But I do know what it is. It's important to know the code that you're writing. So if I try to run this code, the dot operator is saying what's to the left of me is a reference. And I don't care about the reference. I want to go to the object that's being referred to. So this says, this reference, take me to your object. That's what the dot operator does. If you use the dot operator on something that's supposed to be a reference, but instead is null, your program's going to crash with, I'm going to close this one, with a null pointer exception. You're going to see null pointer exception if you're trying to dereference null, meaning you're using the dot operator on a variable that's storing null. That's what your null pointer exception means. So when you see that somewhere in your code, you're doing this, usually not directly like this. If you're doing this, it's going to be obvious to you. You're going to look at it and say, oops, whoopsie. Where mostly this is going to come up, or at least where it bubbles up to the point of office hours, is when you have null pointer exceptions in your tests, where in your testing you're assuming something is not null. You're assuming some property about the list that you're testing, and that property is false. And instead of writing an assert to check the property, you always want to assert the property, not assume. If you're assuming the property, sometimes you'll get a null pointer exception. And because your tests are going to be executed against my intentionally incorrect code in AutoLab. So when your test is ran against my incorrect code, you might be running into some null pointer exceptions. For example, if your test is assuming that the returned linked list is size 4, because that's the correct answer, and your test says returned list.next.next.next.value equals whatever I expect it to be, and then you submit to AutoLab and my incorrect solution returns a list of size 3 or size 2, you're going to get a null pointer exception because you're assuming that the list has 4 nodes when it doesn't actually. It only has 2 nodes. You get a null pointer exception. So I want to say this early and often. Watch out for your null pointer exceptions. Always check for null. We're going to see null checks all day today, all lecture today. So make sure you're avoiding your null pointer exceptions, and that's what your null pointer exception means. You had a null, and you try to use the dot operator. There's no object to take you to, and you certainly can't call a method on an object that doesn't exist. That's your null pointer exception. So that's what that means. So when and if you see that, that's what's going on. I'll still get that question a lot because, well, the whole class isn't here, and someone watching the video on 2 times speed and skipping around a bunch, they're going to miss things like that and waste their own time because they wanted to save some time, and then they'll spend way more hours on the assignment than they're supposed to. It's frustrating to watch every time. I don't like seeing that, but it's such a losing battle. I can't get students to watch every minute of every lecture. It seems, I don't know, it seems like a small ask, but and then what we want to do is add to this list. And effectively what I'm going to do is prepend values to this list. And this line's a little trippy. This trips people up. Is first equals a new node where next is first. So now I'm creating a node where my next value is first, which is a reference to this node right here. So now I have a linked list node with the value 3, where its next is a reference to this node of value 8. And next is null, so this is the end of the list. And then I'm reassigning first to a reference to this new node. The way that first shows up on both sides of the assignment gets trippy sometimes, so I want to explain it. So first is reassigned to this new node, but on the right-hand side, first was still a reference to this old node. So after this line executes, we have first as a reference to the first node in the linked list with the value 3, which has a reference to the other linked list node with a value 8, which has a reference of null, meaning it's the end of the list. If we do this again, first equals new linked list node, let's do -7, sure. First, we can effectively prepend another value. We're prepending -7 to this list. If we run this, I need something else. Let's just print out nothing, just so I have a spot to put my breakpoint. Let's run this in the debugger first. Just doing a lot of live coding. I think we can do more debugger to show what's happening in memory. So first is a reference to some linked list node at 938 in memory, which has the value -7, and its next is a reference to a linked list node at 941. These numbers don't really matter. What matters is these numbers are different, meaning these are two different linked list node objects. The number is going to be different. If I rerun this program, I might get different numbers. It's wherever we got locations in memory on the heap, and they're akin to the OX100 numbers. If this were a trace, it'd be OX100, 200, 300. I say if, but we're about to do the trace, and it will be those values. And this node has -7. A next is a reference to the next node with the value 3, which has a reference to another node, another different node with the value 8, which has a next of null. There's no way to go, there's no arrow here, there's no way to go to the object referred to by this next, because there is none. And a word of caution with memory diagrams is to, I feel like I've been given too many of these already today, but and I've said this one a bunch, but so I'll keep this one brief, but actually trace through the code step by step. There's a tendency, if I give this exact example on a quiz, there's a tendency for students to not trace the code and just write down what they think is going to happen, overthink it, and they'll end up with the linked list 8, 3, -7, and miss the fact that this list is being created backwards. The head of the list is -7, then 3, then 8. But it's easy to miss that if you're trying to overanalyze the code instead of tracing through exactly what it's going to do. So with that, let's trace through exactly what this code does. Garbage. Okay, so let's trace through this and see what it looks like in memory. I mean, we did just see what it looks like in memory in the debugger. Let's do it in a format that we're more familiar with. So every program starts with the main method. We're going to create a variable first. We're going to create a stack frame for the constructor. And I want to copy linked list node because I don't feel like typing it a whole bunch of times. This, I'm always going to put this first so I don't forget to put it on the stack frame. We have an object of type linked list node that we're creating. We're going to map the constructor. I forgot my return arrow. And this object of type linked list node will get copies of all of the instance variables, so value and next in our case. Value and next, which are not initialized. Technically, they get default values. Value is 0 and next is null. Those are the default values, but we don't bother tracing those. If you want to, you can, but I'm not going to force you to memorize what those default values are for every single type. And then the constructor we put on the stack, we got this, which I put here so I don't forget, OX100, a reference to the object that's being created. And then we have the parameters val and next. So we have val and next, which get the values 8 and null. Now we have null, which is kind of a special case. It's treated differently in the code. It's and all that. It's a very special thing. But in our memory diagrams, we just put the word null there. We just straight up null. Why is the first value that's printed at the bottom of the main method? Why is the first value that is printed at the bottom of the main method? Why? What? Wait, what about it? That's not a sentence. Why is the first value that is printed at the bottom of the main method? I can't even. You're gonna have to give me more context there. Why is anything? It's like a philosophical question. Is the way I'm reading it. I'm sure that's not what you meant. So give me some more context so I can help you out. Sorry, I meant that -7 was printed first. Okay, yeah. And this will be a bit more apparent by the time we get to the end of this memory diagram. Thank you for clarifying. It's because the list is created backwards. Yeah, Daniel's got you. Is that we're effectively pre-penning. We're adding values to the beginning of the list each time we add. So at the end, first is going to be a reference to this node with -7, which refers to the node with -3, which refers to the node of +3 and refers to 8. So we're building this backwards. So once we get to this second line, it should be more apparent why it's being built in reverse. Let's finish up this constructor and get to that so I can explain it more thoroughly. So this dot value equals val. This dot value equals val. These are two different names to really emphasize the point that on either side of the equal sign, whenever you're evaluating a new expression in general, each side of the equal sign is a separate expression. You're starting over in the stack frame. So val is starting over at the stack frame. We find val right here with the value 8. So value gets 8. And then this dot next equals next from the stack frame, which is null, which happens to be what it already was, but that's fine. And then we're going to cross this out, and a constructor new and then some constructor call resolves to a reference to the object that was created. So first gets the value OX100. At this point, first is a reference to the first node in the list, and this list is currently just size 1. It's a reference to OX100, a node with the value 8. Next is null, indicating that it is the last node in the list. Then we get to this line where things start coming together. So we have another constructor call. We're running the same play. This, so I don't forget, it returns to first. We create a new object on the heap. It's going to have two instance variables, value and next, which are not yet initialized. We got OX200 for this. We have two constructor parameters, val and next. Val gets 3, next is first. So first, we have to evaluate this first. 1, it's inside the parentheses. 2, it's on the right-hand side of the assignment operator, so it has to be evaluated first. And 3, like we can't assign first. We can't change the value of first until we get done with this call. Like we don't know what value it's supposed to get yet. I guess technically we do. It's going to be OX200. But that doesn't happen yet. We have to evaluate the constructor first. So at the point of the constructor being called, first still has the value OX100. So that's what we give to the constructor. This will be OX100. Even though it's about to change, at this point in time that we have to evaluate this argument, first store the reference OX100. So the constructor is going to give 3 and OX100 to its object. This returns, and then when it returns, this whole thing resolved to a reference to the object that was created, which was OX200, and then that's what's assigned to first. So first gets reassigned the reference OX200. And this is how the list is being created in reverse, because after this whole line executes, this whole statement executes, first is now storing the reference OX200. So if we follow first and track our list, we have first is a reference to this node, which has a value of 3, and a next of OX100, which has a value of 8, which has a next saying I'm the end of the list. So right now the list is 3 and then 8 in that order. So that's how we're pre-penning to the beginning of the list, because we're replacing the variable that stores the first node in the list with a new node with a new value, and then having it refer to the rest of the list of whatever else was already in the list. And then we do it again. This, so I don't forget. My return arrow, constructor, linked list node, instance variables, value next. We got OX300. We got our constructor parameters, val and next. Make sure you're only putting in the stack frame the constructor parameters for a constructor call. There's a tendency for students to take every instance variable and stuff them in the stack frame for the constructor. Don't do that. Don't be that person. Don't do it. Oops, fail. As I do exactly what I just said not to do. We're taking the constructor it's because I had them highlighted. We're taking the constructor parameters and putting these and only these on the stack. Now I have I think this is partly my fault. A lot of the examples from here on out, the constructor parameters exactly match the instance variables. So then students just get stuck in that pattern of thinking that, oh, the constructor parameters will always match the instance variables, so that's how I'm going to trace it. The first ones we did, all the ones we did on Thursday, did not follow that pattern. But then moving forward from that, I tend to use the constructor to initialize all the instance variables in my examples, and I feel like that's where we get some confusion. So heed my words. Don't do that. Do what the code tells you to do. The code tells me to put val and next on the stack, and that's why this is val and not value. And this is why I named it something different. This is val, not value, because it's the constructor parameter. The constructor parameter was val. Value, the fact that the instance variable is called value, has absolutely nothing, absolutely zero to do with what goes on the stack. The instance variables have to do with what goes in the heap. The constructor parameters, those, just like any method call from 115 onward, the parameters will go on the stack with that stack frame. So hopefully none of you make that mistake on the quizzes. It's a crappy way to fail a quiz too, to mess up your stack frame parameters. That alone, I would still pass, but students will often do that, and then that will cause them to make more mistakes later on that are critical. This returns OX300 to first. And we reach the end of our program. We're not going to cross out the main stack frame yet because I'm going to add to this example, and we'll come back to tracing this. But I want to show creating a linked list first. So the variable first now has OX300. So it has a reference to this node. This is now the head of the linked list. This is the first node of the linked list. So the first value is -7, which has a next of OX200. So the second value is 3, which has a next of OX100, which has a value 8, which is the end of the list. So now the list is -7, 3, 8 in that order. So if you're tracing through the code, you go through the trace like this, you're not going to mess up the order of a linked list. But it is not intuitive. It's not intuitive when you first look at the code that this list is being created backwards. But hopefully the trace makes it a lot more clear what's actually going on there. If not, well, we got more examples. What was I had a thought. I lost it. And I've already said pretty much everything I need to know about a linked list fundamentally. Now we want examples, we want to reinforce things, and primarily we want to talk about a whole bunch of algorithms that we're going to write that work with this structure. So great, we have this structure, now what? That's pretty much the rest of lecture, is writing algorithm after algorithm to be able to work with linked lists. Because just knowing the structure is one thing, but how in my code am I going to use this linked list to actually do something useful? I gotta take a quick break. I gotta let my dog in. He's scratching at the door. I'll be right back. we back. Okay, so let's jump back to the code and write our first algorithm. Let's stop this and close it. We'll write our first algorithm, which is going to be something we've seen very briefly last time, is a toString method. So let's write a method that's going to help us print these values to the screen, because right now, if I print out first and run this, well, not now because I wrote a toString, it's going to give me that default, just fully qualified name at some value. I don't want that. I want something actually meaningful printed to the screen. So let's give this a toString method, which is going to return all of the values in the linked list separated by spaces. That's the method I want to write, and in the order in which they appear. So to do that, I need string, call this toReturn. I'm going to call that toReturn. And be consistent. The slides aren't consistent. toReturn, and I want this dot value, but value is not a string, so I'm going to get an error if I do this. I'm trying to assign an int to a string. I'm trying to assign an int, a value of type int to a variable of type string. That's not allowed. There are some cheesy ways to do this, to get around this issue. One, the concatenation operator we saw will auto-convert to strings. So if I just have an empty string and then concatenate this value, this dot value to it, it will, the concatenation operator from the string class will actually convert that value into a string. So I can do that. I can also do, I can also do string. I think I did this in a previous lecture. String.value of will also get us there if we want to be a little fancier with it. But I'm not feeling fancy today. I'm just going to do empty string plus and just let concatenation take care of it for me. And then I want to get all of the values of the linked list concatenated together. And to do that, and what I'm going to do all lecture today, I'm going to use recursion. So let's talk about recursion again. It's coming back in a big way today. We're going to use a lot of recursion. So so to get the rest of the values in the list, I'm going to recursively call toString and continuously append to get one final string. To do this, I need a base case. If we're going to have recursion, I need a base case that doesn't make a recursive call. And that base case is going to be if this dot next equals null. So if we've reached the end of the list, I don't want to do any, oh, actually that's not, yeah, no, that's fine. If I've reached the end of the list, I don't want to do anything. There's nothing more to do. There's no recursive call to make. But if we haven't reached the end of the list, if the next is not null, and this is going to be common in everything we do with linked lists, we're going to have our null checks. This is our first of many, many null checks that we're going to do. Our null check, we're going to see, am I at the end of the list? If I am, I want to do one thing. If I'm not, I want to do something else. That's what all our algorithms are going to look like. So if I'm not at the end of the list, then I want to do toReturn. I'm going to use plus equals, which is concatenate equals in this case. A space, because I want all the values separated by spaces. And then plus this dot next dot toString, my recursive call. And let's get our return statement. I named this variable toReturn because it's going to be what I return. If you see like toRet or toReturn like that, it means it's a variable that's building the answer, the eventual return value of the method call. Just annotates the code a little better, in my opinion. So if we're not at the end of the list, we want to make a recursive call. We're going to ask the next node to convert itself to a string. It's going to convert itself to a string and resolve to whatever it is converted to a string. Then we're going to append the space and then toReturn, which is the value at this node, add that value to the beginning of the string that's returned. and then return that value. And then print line is going to call toString implicitly. If this were a quiz, or if you look at the slides, what I would do is string str equals first dot toString. I would make the call explicit and then print. Actually, I'll trace it like this since that's the way it is in the slides and everything. I would make the call explicit just to make sure. I've had problems in the past where I had an implicit toString call, and some otherwise very good students who absolutely could trace toString just either forgot to or thought that they didn't have to. Because very often in lecture I say, any method that's internal to Java, you don't have to trace. Print line's internal to Java, so you don't have to trace it. Very reasonable logic for a student to follow. And I couldn't even get mad at them. I'm like, yeah, that makes sense. I see why you did that. And then I gave them credit. But since printline will call your toString method, which is not internal to Java, you would still have to trace that. So I like to be explicit these days and very clearly say, hey, look, toString is being called. Make sure you trace it. So let's get this code in here and do exactly that. Let's trace it. Need my toString method. Add to this example and just pick up our trace. We're creating the same linked list, and we're just going to pick up our trace right here at the next line. So let's create our str, which is going to get the return value of a toString method. I know there will be a this, but I don't know what it is yet. Let's look at the code and see what the code tells us to do. We have first.toString, so first, which is OX300, dot means take me to your object. ToString means call the toString method from this object right here. This is the calling object. So this in the stack frame is a reference to the calling object OX300. And then we run the toString method. So we have a local variable toReturn, which gets the value empty string concatenated with this dot value. This dot value is -7, so we get -7 printed to the screen. Oh, actually I wanted to, since we're doing live coding, I want to show what this will do first, just to show that it will do what we want it to do. It's -7 space 3 space 8, so it's all the values in the linked list separated by spaces. And we did one nice thing about recursion with this very specific thing that we want to do is with recursion it's trivial to get the spaces in between the values. If you want a comma separated list, like we could do that, we'll just add a comma right here. We'll get a comma separated list. Exactly with the commas where we want them, with no trailing comma, no leading comma. We don't have to have extra logic to say if this is the last value, don't add the comma. The recursion just works out for us that way. It's one really nice thing that recursion gives us for a very specific application of converting a sequential data structure to a string. Okay, so we were right here. Here's the nice thing about traces is I actually forgot what we were doing, but I look at the last stack frame, look at the values, and figure out where we are. We just did toReturn. The trace tells me exactly where we left off. So now if this dot next equal null, so this dot next does not equal null. It has some reference. I don't know what the reference is or whatever. I just know there's a reference to an object here. So we're going to hit the else toReturn plus equals space plus this dot next dot toString. So the first thing we have to evaluate here is the recursive call. We're making a recursive call to toString, and we're actually doing something a little tricky here. Where we know we have a call to toString. We know it's going to have a this. My mic's right there. I couldn't see. We know it's going to have a reference this, but we don't know what it's referring to. So let's take a look at it. It's this dot next dot toString, or dot, oops, I missed my dot, dot toString. So we're calling toString from this node right here. So the tricky thing we're doing is actually advancing through the linked list using the reference stored in this. So this is going to be the next node in the linked list. And we're moving through the linked list because of the way we're making the recursive calls through different objects. We're making the recursive call through the next node. So this is going to be a reference to the next node. And that's keeping track of which node we're currently processing in the toString method is by using the keyword this. And the only reason we can do that is because we're inside the linked list node class as we're traversing the list. As we go through these examples, we're going to get to an example where we are not in the linked list node class. And I'll make a big deal about it when we get to that one. We got 3 more examples after toString to do before we get to that. We're not going to trace them all, so we will get through the next 3 a bit quicker. But we will get to one that's not in there, and we're not going to be able to use this trick. So just keep in mind that we are using the keyword this is a little bit of a trick to be able to traverse through the data structure. And let me get the value. This dot value is 3 as a string. I messed up my -7. This is a string. I messed up my 3. That's a 3, not a hashtag. And with recursion, remember with recursion, we always have to have a base case that doesn't make a recursive call, which we have right here. And also, all of our recursive calls need to get closer to that base case. So if each recursive call is advancing one node through the list, through this, the reference this, and that means we are advancing closer to the end of the list, and that's exactly our base case, is when we've reached the end of the list. So it looks like we have all our ingredients for some good recursion here. And then each stack frame is only concerned about processing a single node. That's one of the advantages we get from recursion here, is each stack frame only has to worry about one single node, not the entire list as a whole. We're just processing one node and passing the rest of the work off to a recursive call to the next node. So that's exactly what this node's going to do. This dot next is not null, so we're going to hit the else. We're going to have to make this recursive call before we can evaluate the rest of this line. So we're going to make the recursive call to toString, where this is going to be this dot next dot toString from this stack frame. This dot next dot toString, we're calling toString from this node right here, OX100. So OX100 is our this. We get to return, spelled not like that. To return is going to be this dot value 8 as a string. 8 as a string. And we're about to hit the base case. Let me take this question. How do we create an empty linked list? We will get to that in a later example, so I'll give you a brief answer right now. Is we would store, actually I can do it right here. We would store null. So say we wanted first to be a linked list. We just straight up null. That's going to be our representation of an empty linked list node. There are different ways to do that in different languages, depending on where you are, what libraries you use, and all kinds of different variables. But in 116, this is going to be our answer. We're going to assign the variable itself to null. Within the linked list node class, there's no way to represent an empty linked list. But when we have a variable of type linked list node, we set that variable itself equal to null. That's going to be our linked list, our empty linked list. So like in your song class, when your list has to initially be empty, just set your instance variable equal to null. Okay, so we're going to hit the base case here. We're executing this code. We're on this line right here, this dot next. This dot next is null this time. So we hit our base case. This is going to do nothing. Importantly, it's going to skip the else block and not make a recursive call and go right to the return of to return. So this stack frame is going to return its value 8 as a string. So it's going to return. That value is returned right here in the previous stack frame. Since this isn't being returned directly into a variable, I don't have my return arrow. If you want to do your return arrow, if you have to trace this code for a quiz and you do your return arrow to return, if that helps you think about, keep track of the trace, that's fine. I ain't gonna be mad at that at all. But since it's not stored directly to a variable, we technically don't draw a return arrow into a variable because there's extra processing to be done here. So I'm not going to put any return arrows. So this stack frame was waiting for this recursive call to resolve, and it did resolve. This resolved to 8 as a string. So it's going to take 2 return, which is 3, concatenated equals space, and then what was returned. So it's going to get the value 3 space 8 as a string. That's what toReturn is, and then the next thing this stack frame does is returns that value. So we're going to return 3 space 8 to the previous stack frame. This stack frame was waiting for its recursive call to resolve. This resolved to 3 space 8. So we have -7, then a space, then 3 space 8. So as a string, -7 space 3 space 8. And then that stack frame is going to return all the way back up. Here we do have a return arrow all the way up to this variable right here, -7, 3, 8. So if you do your return arrows when it's not directly to a variable, you might be tempted to just write the value right in there and forget to do the extra processing. Since there's extra processing, it's no return arrow. Okay, and then we print that to the screen. -7, 3, 8. Okay, and there's our trace. And this is the only linked list trace that will do. Excuse me. This is the only linked list trace that will do. Mostly because there's not enough time to load up on linked list traces. But this shows everything we need to see how a linked list is mapped in memory, how to traverse a linked list, how to do the recursion. And I do argue, that we didn't learn anything new with this trace. If you can trace, we did learn something new because we're talking about linked lists through a trace, so we can visualize what a linked list does. What I mean by that, though, is that we didn't learn anything new, is that if I gave you this code as a trace, and in fact, I'll go a step further. If I gave you the data structures quiz from the midterm right now, the 2 data structures quizzes, you should be able to do them. I think that would be false. I think the failure rate would be way too high if I actually did that because you need more time to study. But you have everything available to you to be able to do the data structures quiz because it's all a combination of objects, creating objects, calling constructors, manipulating references. Like, we didn't do any new concepts here. We've done recursion before. We've done object creation. We've done objects on the heap that have references to other objects on the heap. We had a party class that had a reference to an array list that had multiple references to other to character objects. We've done all that. So you have seen all these concepts. They need to be reinforced a bit more. You need time to study and stuff, sure. But you have seen all this stuff to the point where I theoretically should be able to give you this at the beginning of lecture today without talking about linked lists at all. You should be able to trace this. It's more advanced than anything we've done so far, so that's a little bit of a stretch. But talking specifically about the concepts that have been covered, there's no new concept that you haven't seen here. It's a new combination of those concepts, so it is still kind of new and fresh in that sense, but there's no new concepts that we covered here. And my other note, I gotta make sure I say this or else I'll forget, but I encourage you to use recursion. Many of you, just historically speaking, many of you won't use recursion on task 3, and I mean, that's allowed, it's fine. I'm not going to take away credit or anything, but I do recommend that you use recursion to get practice with recursion, because when you get to task 5 with trees, you will be using recursion, because using a loop to traverse a tree is way more work than with recursion. And I haven't seen anybody who actually went through the trouble of using loops because it's so much more work. It's so much more advanced to be able to do that. That recursion makes that so much easier. So if you get to task 5 and recursion with trees, which is a bit more complex than recursion with linked lists, if that's the first recursive methods you're writing, it's going to be pretty hard to write those methods. But if you have practiced writing recursive methods with linked lists from task 3, it's going to ease you into those recursive methods on task 5 a little bit easier. It's going to be a little bit, it's not going to be as overwhelming when you get to task 5. So that's my pitch. I encourage you to use recursion when you're working with linked lists. But if you don't, and then task 5 takes you way longer than you want it to, just know that that's the trade-off you're making. It's okay if you want to make that trade-off, you want to make your own decision, go for it. But that is the trade-off you're making. Task 3 gets easier, task 5 gets harder if you don't use recursion on task 3. But a lot of students, especially if you're struggling with task 3, I get it. You just want to get task 3 done in the moment, especially with the expected deadline coming so fast. Oh. I got that. Oh, there it is. All right. Are we on time? Not bad. Okay, so let's write some more methods. I want to write 3 more methods. I want to write a size. I have to double check one thing. There's something. No, I don't think there is, but I just got to double check to make sure I'm not going crazy. Oh my goodness, I am. I'm totally forgetting something. I am going crazy. Before we get into algorithms, we got a big thing to cover. It's kind of a side note, but it's something we got to talk about. And I can't believe I almost forgot. I would have remembered by the time we got to one of the other examples because I would have got all jammed up and then remembered. But good thing we're getting it right now. Is what I want to do is something like this. Numbers equals I want to do something like this. And more specifically, I want to do this. With an array list, when I create an array list, I don't just create an array list. I create an array list of some type. I can specify integer, I can specify string, I can specify, wrong package. I can specify character, I can specify any type I want for array list, and I can create an array list of any type that I want. Even types that didn't exist when the array list class was created. I want that flexibility with my linked list node class as well. That's what I would very much prefer, to have this type of flexibility. And we've seen this on the user side. We can use this thing called type parameters that we're going to talk about here. We can use these type parameters on the user side, but how do we write a class that's going to allow for type parameters like this? How are we going to get our linked list node class to have this same flexibility? So let's do that. Java calls these generics. C++ calls them templates, for what it's worth. I'm going to call them type parameters. I think that's the best language agnostic term to use because it's the most descriptive thing, in my opinion at least, because it's a parameter that is a type. And the way we specify type parameters is right in the class header, linked list node. We're going to say linked list node of, and I'm going to say T. This says that the linked list node class takes a type parameter, and I'm going to give it a variable name, and that variable name is going to be T. I can use whatever I want. I can name this variable whatever the hell I want. The green underline says you have a typo, a misspelling. But typically, our type parameters to follow convention, so the language won't be mad at me. The language won't even be mad if I start it with a lowercase letter. But by convention, if you want other developers to not be mad at you all the time, we name these with one single capital letter, and I'm going to choose T for type here. One single capital letter, that's the convention. So if you see one single capital letter as a variable name, you know that that's a type variable, a variable that's a placeholder for a specific type. Oh, it does call it type parameter here, but Java, the language, calls them generics. It's nice to see type parameter in the IDE at least. And if we go to array list, we can see it calls it E, just a capital E, one single uppercase letter for their type parameter. If we create a hash map, I'm not going to create it, but let's just go to the class. They use two type parameters, one for the key, one for the value, and they're named K and V for key and value. But single uppercase letters, that's the naming convention for type parameters. But note that this is a variable, and we can change its name. What I want you to not do, because I haven't seen someone do this in a while, so don't be the first one to break the streak, is on the homework, what you'll be doing is creating a linked list of ratings as part of the song class. When you create that linked list node of ratings, do not change this to rating, because that doesn't do anything. All you're doing is changing the name of a variable, which has zero effect on the functionality of your code. Leave this as T. Don't change the linked list node class, except as I'll mention later, you can add the append method because it's not in the handout. But don't change this in the linked list node class. What you want to do is change it when you create your linked list nodes. So with this linked list node, I'm going to have this as a linked list node of integers. Oops, I actually missed the shift there. And since it's a type parameter, I do have to use the capital I integer. I can't use the lowercase I int, the primitive, anymore. And I need my same syntax as with array list. I can put integer here, but the IDE is going to say, you don't need to do that. It's implicit. You don't have to tell me twice. I already got that it's integer because you told me right here. So we usually leave this side blank, but we do need the type parameter, rather type argument list in our code as well. So we took a type parameter, we don't use it yet, and then we're going to go through our code, and wherever we need a value of that type, we're going to replace it with T. So we're not going to have our value just be int, hard-coded at int. We're going to have it be whatever the type parameter is. So we're going to have a value, an instance variable value of type T, a parameter of type T, a linked list node of T, and a linked list node of T right here too. So we're going to replace wherever we use that type, we're going to replace it with T, including as additional type parameters that we're sending to other variables. So now we have a generic linked list. And if I want to create another linked list, if I want a linked list of strings, I can give it a type parameter string. New linked list node. I don't have to specify string twice. Name. I blanked on something more interesting there. And I can create a linked list node of string as well, and then prepend strings and do all my linked list node stuff with that. And importantly, I can have a linked list node of ratings, which is required for task 3. That's what you'll be doing in task 3. So now I have a lot of flexibility. We like the flexibility of type parameters, so we can write the linked list node class one time and have it be used for any type. Doesn't matter what type you're storing here now. It just doesn't matter. It can be stored in this list, and all of our methods are going to work with whatever type we get. So let me clean up a little bit of this. And that's type parameters. So type parameters, very important, very useful. Also, it's not write too much code. Or else for the homework, you would be creating a linked list node ratings class, duplicating all of the work we did on a linked list node here in lecture, but replacing int with rating everywhere. Instead of that, we're going to take a type parameter and just take any type at all and have our code work for every type. Okay, now with that, we're actually ready for these algorithms. We want to write 4 algorithms: the size method, a I remember what it is. I append, find, and then kind of, we're going to go to another class for this one, but min of a linked list of doubles. And this last one is the most important one in the terms of your homework. We're going to have these 3 and 2 string. These 4 are building up to that just so we get used to the structure of a linked list. And then we're going to hop out of this class and create a new class to do the min of a linked list of doubles. And that's the one that really corresponds to, did I just say this? That corresponds to what you'll do on the homework. Okay, so let's just do these one at a time. Size, public, int. So we want a method where you can ask for the size of the linked list, and it tells you how many elements are in that linked list. So int size shouldn't take any parameters, and it's going to be recursive. And when we write recursive methods, we want to break this into our base case and our recursive call. And with linked list, almost always, I can't even think of any exceptions, always in 116, our base case is going to be the end of the list. So if this dot next is null, return, we got to figure out what we're going to do. If next is null, and here's another thing about recursive methods, is you're creating a lot of sub-solutions to sub-problems. So if next is null, we're not returning the entire size of whatever list we're a part of, because this node has no idea. It doesn't know anything about the list as a whole. So what we're going to do is solve the partial solution of whatever node size was called on, which is this. What would be the size of the list if that node was the head node of the list? So if this node was the end of the beginning of a list, what would be its size? And if its next is null, oops, we're just going to return 1. So if you ask a node, hey, how big of a list are you? And it looks at its next and it says, hey, nobody's after me, so I'm 1. Yeah, I'm just 1. I'm just a list of size 1. Else we have the recursive call. When you make a recursive call, what we actually do, which always seems strange at first, is we know we're gonna make a recursive call, and we're gonna ask the next node in the list, hey, next node, what's your size? And the part that seems weird is we're gonna make a recursive call, something that gets us closer to the base case. For the case of a linked list, we're gonna move 1 node down the list, and we're going to assume that the recursive call returns the right answer. Even though we haven't even finished writing the method yet, we haven't really done anything, we're just going to assume that it returns the right answer. So if we're somewhere in the list, let's say we're the first node even. We're the first node in the list, and we're trying to figure out how large the list is, we're going to ask the second node of the list how big it would be if it were the head of the list. That's what size is going to return, is the size of the list, treating as though this is the first node in that list. So the last node of the list is doing that. It's pretending it's the first node and it's returning 1. So we're going to assume that we ask the next node how big of a list we are, and it does return the right answer. We don't know how it's going to do it yet, but through the magic of recursion, we just assume it's going to. So if I refer to a list of some size and this returns the correct size for my next node, then me as a node, as a list, must be that size plus 1. So it's going to ask the next node for its size and then add 1 to it. And that's the end of the method. So when you're writing recursion for linked lists, the method itself only needs to process 1 single node. So we're either just telling the answer directly, or finding a sub-answer via magic, and then adding 1 to it to process that 1 node. And then if we print this to the screen, we'll just print first dot size. We should get 3 printed to the screen. And like I said, we don't have time to do memory diagrams. If you want, I have visuals in the slides that walk through these a little bit, but we're doing live coding style in the 11 a.m. lecture. So I'm going to use the debugger and go through some live debugging to show what's going on here. So with the debugger, we're going to go into the size method. And we're asking this. Oh, and once you have a toString, by the way, the debugger will call toString to visualize your data a little bit easier. So we're going to check. If this.next is null, which is false, the debugger's blatantly telling us that it's false, we're going to go to next, and we're going to say next.size. So we're going to ask the next node, hey, how big are you? So we're going to say, hey, second node in the list, how big are you? What's your size? And it's going to go, well, my next isn't null, so I don't know. I just don't know. I'm going to ask my next node what its size is, and hopefully it knows. So it's going to ask its next node. Now we're at the node that just stores 8 and null is next. So next is null, and this node says, hey, I know my size. My size is 1. It's only me, baby. I'm the only one here. And it's going to return 1 back to the other. Oh, I have my stack frame squeezed. Back to the stack frame that called it, which is this node with the value 3. Where's my... Can I get all this on screen? Which is the node with the value 3. So this node here is the last node in the list, and it returned 1. It said, I'm the only node that exists. So it returned 1. And then now we're back in this node, the node with the value 3, which refers to that node with the value 8 and null as its next. So this node gets the value 1 from this.next.size. This resolved to 1. It's going to say, okay, well, if you're the last node and you're just size 1, let me count for myself and add 1 to that and then return 2. So it returns 2 to the next stack frame. Now we're at the first node in the list, the head node, -7. And it just got the answer 2, which was the correct answer. The magic of recursion held up for us. And this.next.size correctly returned 2. And then this node is going to say, well, if you're size 2 and I'm referring to you, I'm an extra node, so let me account for myself and bump that up by 1 and return 3 back to the original caller, and we'll print 3 to the screen. And if there were more nodes, we would return 3, add 1 to 4, add 1 to 5, add 1 to 6, and effectively each node is counting off. The last node says, I'm just 1, and then all the rest of the nodes just say, okay, I'm 1, I'm 1, I'm 1, I'm 1, and we're adding +1, +1, +1 for every single node through each recursive call, through each stack frame. Each stack frame adds 1 and accounts for each node, and we get the total number of all the nodes by the time we're done with all the recursion. Magic of recursion. So let's do more recursion. So append. When we created our first linked list, we effectively pre-pended. We're creating a new linked list with size 1 and then pre-pending our values to the beginning of that list and building this list in reverse effectively. Usually what we want to do is add values to the end of our data structure. That's what we do when we call add on an array list. That's what we're used to. So let's write that method and do public void. We don't have to return anything with append. Append. And we want to append some value. That value is going to be of type T because we're using type parameters. And I'll call it to add, the value we're going to add. And the difference between append and prepend, the extra stuff we have to do, is that with prepend, we already have a reference to the first node in the list, so we can just directly prepend. It's really easy to prepend to a linked list. With append, we have the extra work of having to find the end of the list first, which we don't have random access. We can't just jump to the end of the list. What we have to do is for each node, ask for its next node. We have to do .next, 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 go through the entire list until we see null. And once we see null, then we know we've reached the end of the list. And we might be bouncing around in memory for a while. If this list has 1 million elements, we're bouncing around to 1 million different objects on the heap and constantly following the references. And there's no way to shortcut that. Well, I shouldn't say no way. When we do queue, I'm going to show you a way. But there's no great way to We don't have a way yet to make that any more efficient. And there's no generic, general way to make that more efficient. If you have linked lists, you got to bounce around memory at some point in time, depending on what exactly you're doing. Okay, so we got to find the end of the linked list first. All our recursive methods, our base case is, are we at the end of the list? Well, if we're already at the end of the list, if this.next equals null, then we are at the end of the list. This is the last node in the list, and we've found a home for this value we're going to add. So we're going to replace that null with an actual node, a new linked list node with the value that we're adding, and a next of null because that node is now the new end of the linked list. So we found the end of the linked list. This is the last node of the linked list because its next is null. We're going to replace that null with an actual node, and that node's next is null, and its value is whatever we were trying to add. So that's the best case. That's the base case, and it's the best case because it's where we actually get to finish the job. We're going to add the value. If we're not at the end of the list, we're going to make the recursive call. And this recursive call is one of the simplest ones. This.next, we're going to tell the next node to append this value. So if we're not at the end of the list, so any node that's not the last node in the list is going to say, hey, next node, my next node, add this. You take care of it. Because I'm not doing it, you do it. It's going to pass the responsibility on to the next node. Then it's going to pass it on to the next node, to the next node, to the next node, until we finally get to a node that says, oh, shit, there's nobody else to pass this on to. I guess it's my job to add this node. And it's going to say, okay, I'll do the actual work. All you other people are lazy, you didn't want to get it done. I'll do the adding, the actual appending of this node. And it'll append that node. And notice this returns void. There's nothing to report back to the original caller. There's nothing to report back. They called append, and they're just going to have to take it on faith that append actually did append the value. Just like when you call add on an array list, you don't need any return value. There's nothing that it returns back to you. You call add, you trust that add does actually add that value to the end of the array list. So same with append. Let's just keep plugging away. So public, we want to find the first occurrence of a node that contains a particular value. That's what we want to do in this one. And we'll actually, dare I return a Boolean? I'm going to return a Boolean. In the slides, I return a reference to a linked list node. I actually return a reference to the node that we find. But we never, which is something you'll see a lot in practice, but it's something we never use in 116. So I feel like it just causes more confusion. So I want to do find, and I want to find some value t. I'm going to call it toFind. This is the value we're trying to find. And we want to return true if we find it and false if we don't. In the slides, if you look at the slides, this will return a linked list node of t, and it'll return a reference to the first node that contains that value, which is often useful. You often want a reference to some node of interest because you want to manipulate the references. You want to change its .next or do something with it. But here, we're just going to return a Boolean and cut one distraction out of here. So we want to find this value. Here we have our base case of I never called append. Let me call append and mess with this list. We can keep toString, but let's do first dot append 12 first dot append. So we have much cleaner functionality now to be able to get more values into this list. Let's run this, and we should see those values at the end of the list. So now we have our original list, and then we appended 12 to the end and appended 100 to the end, and we can see our new size is now 5. So everything's working the way we want it to work, the way we expected. And if we run this in the debugger, let's debug appending 100. So we're going to ask the first node. We're going to say, hey, first node, which does have 12 already appended. Hey, first node, can you add this? And it says, well, my next isn't null. I'm just going to tell the next node. I'm going to tell the next node, the node with the value 3, I'm going to tell it to append this thing. So the node with the value 3 says, well, my next isn't null. I'm not the end of the list. Node with the value 8, you do it. I ain't doing it. Node with the value 8 says, well, my next isn't null. I have another node after me, so I ain't doing it. I'm going to pass this task on to the next node. And this, notice our reference for this is updating in all these nodes. This is a reference to a different node each time. With this last one, the node with the value 12, it looks at its next and it says, my next is null. I'm the end of the list. The buck stops here. I better get the job done. It's going to assign its next to a new node that's being created. I don't want to go through the constructor call. And then its next is now replaced with a new node that it just created with the value 100 and a next of null. And then it's going to return. Each stack frame just returns. The debugger just returned all those stack frames for me without me having to click through them. And now my new list is the old list, but with 100 appended to the end. Okay, now let's find. So we have our usual base case. If this dot next equal null, else. But we actually have an extra base case. So somewhere in here we want to check if we found this value. So I'm actually going to add a second base case here, which says if this dot value equals the value I'm looking for, return true. And then else if the value, if this node does not contain the value I'm looking for, like if this node contains the value I'm looking for, I'm done, return true, we're out of here, we found the value, we win. Good job. If we don't have the value at this node, we're going to ask another question. Is this the last node? If it is the last node, we want to return false because we went through the entire list and did not find the value to return true. So therefore, it's not in this list. We didn't find it. And else, if it's not either one of our base cases, then we're going to return whatever our recursive call returns when we pass the job on to the next node. So this dot next dot find, whatever that node returns, which will be one of our base cases. We're going to eventually hit one of these two base cases. Either we find it or we don't. And we're going to return whatever the next node returns. So let's go back to our list. Let's just print them to the screen. First dot find 8. First dot find 9999, and first dot find 100. I actually want to go through 3 examples of this. So we should have true, false, true. So let's make sure we get the right output first. True, false, true. Looks good to me. And now let's run the debugger. I'll go through this fairly quick once it starts getting repetitive. But we're looking for 8. We're going to check, does this dot value is -7? Does that equal to find, which is 8? No. So that's going to be false. Are we at the end of the list? No, we have a next. So we're going to make a recursive call and just pass the buck down to the next node. The next node is the node with value 3. That is not 8. Next is not null. So we're going to pass the job on to the next node. The next node has value 8, which is equal to 8. So it's going to return true. And all the other stack frames are all just going to return true. And that propagates all the way up to our initial call. And we print true to the screen. 999. We're going to do the same idea. We're going to go through each node. It doesn't have the value we're looking for. And the and it's not the end of the list. So we're going to keep going through each value until we get to, oh, I clicked right through it, until we get to the end of the list. And the end of the list says, well, my next is null. I didn't find what we're looking for, and my next is null, so it's not in the list. Sorry, didn't find it. Same thing here. We're going to go all the way to the end of the list until value is 100. This is going to return true, and we get the value that we're looking for, and we get true, false, true printed to the screen as we wanted, as we expected. The reason I wanted to go through all three of those is the order here really matters. So if we do these out of order, if we're not thinking too much of it and we're like, well, the base case is always the end of the list, so let me write that first. If we're at the end of the list, that means we didn't find it. And then we're going to check if we found the value and return true, yada, yada. If we do that, we're going to get true, false, false. This is one of our edge cases that we have to be careful of, because when we get to let's see how I can quickly get to it. So when we get to I closed out the debugger. Because the first one finds it. Oops. Okay, so when we get to the last node, so we're finding 100, which is at the last node in the list, and we're at the last node. It has value 100, but the order here matters. So if we're checking if we're at the end of the list first, what we're missing is processing the last node in the list. So we're saying next is null, so therefore it's not in here, but we do have the value. The value we're looking for is exactly the value at the last node of the list, but since we're doing our null check first, we're just returning false without ever checking the value at the last node. So make sure you get your order when you need something like this, which you do need in the removing a node on the homework. Make sure you're doing your checks in the right order. Make sure you process the node first and then check for null, for next being null, to make sure that that last node is checked. This is one of your edge cases with linked lists. If the node of interest is the last node of the list, if it's the first node of the list, or if it's in the middle of the list, those are the three big test cases that you should have. Yeah, honestly, with just those three, you should get there. You should satisfy all the testing in Autolab. But make sure you have a test for the first node of the list and the last node of the list to make sure you don't have bugs like this, because I will have an incorrect solution in Autolab that does exactly this bug, has exactly this issue. So the order does matter when you have multiple base cases like that. So let's fix this and get it back to the way it was. Okay, how are we doing on time? Not terrible. But this next one's going to take a lot longer than it does in the other lecture, since I have to code the whole thing. It's a bit to code. Length list of doubles. So with all of the examples that we've done so far, I'll leave the text there. With all the examples that we've done so far, we took advantage of the fact that our recursive call is going to have the keyword this storing a reference to the next node in the list. We're using the keyword this to advance through the list in the next step of each recursion. And we're only getting away with that because we're in the linked list node class. In fact, we're also accessing private instance variables because of that. And we can do .next and .value because we're inside the linked list node class. So I'm kind of cheating there. I'm also cheating in, actually, let's fix that one first. So I'm kind of cheating there, that we're not going to have access to these instance variables, these private instance variables outside of the linked list node class. And for your task 3, you're going to be inside the song class, which notably is not the linked list node class. So you can't do just .next, .value. And you can't use the keyword this, because this is going to be a reference to a song, not a linked list node. So you can't advance to the next node using the keyword this. So none of that stuff we can actually do on the homework. The whole point of these was to show you refresh recursion and get used to working with linked list, getting your null checks in the right order. That's why we still want to do these examples. But this next example is going to very much so mirror what you're expected to do on your homework, on your task 3. So first, let's just get our getters and setters. So public t get value, get value, which is going to return this dot value. Public linked list node of t get next is going to return this dot next, and public void set next is going to take a linked list node of t, so I'll call next, this dot next equals next. And with getters and setters, it's all about control. That's why we use getters and setters. And part of that control is sometimes you don't want people to mess with your variable at all. So for this example, I'm going to say I don't want anybody changing my value of a linked list node. After they call the constructor, I don't want them ever being able to change value, this instance variable. So how am I going to restrict that? Well, I just don't give them a setter. If I don't write a setter, you can't change that value. Easy day. And the warning here is actually that this can be final. So I can make this final. Get rid of the warning. I'm not going to do that because I feel like that's a distraction from linked lists, from the linked list lecture. But that's what the warning is telling me, is that I can make this final since there's no way to ever change value after the fact. And nowhere in my code do I change value. There's sometimes useful reasons to do this for this very specific thing is if you want to maintain a sorted linked list and letting people change the value. If somebody changes the value after it's sorted, you might not be sorted anymore. So you would restrict them from changing the value, so now they can't mess with it. Also, set next, you have to get rid of set next as well, so they can't mess with the ordering. And then you can actually guarantee that the list does remain sorted. Okay, so we have our getters and setters, and there's one other thing. We'll circle back to what we're going to do about not having the keyword this available to us to advance to the next node, but we'll do that in the new class that we just created. The other issue that we have is this right here, is dot equals. I just snuck this by without really talking about it. Also, the implicit toString call right here. These are two things that we used that are kind of cheap, kind of cheating, kind of limiting. Like what we did here is pretty much all we can do. So the issue here is that we're calling a method through value, and value is of type t, and we don't know what t is. We don't even know what type value is going to be when we call these methods, this implicit toString method and the equals method. We don't know what type we're calling these methods on. So how do we know that whatever type we get is actually going to have those methods? How do we know that it's going to have an equals method and a toString method? Well, the reason we know that is because every object in Java, every object ever, every single one of them has a toString method and an equals method. So there are these special methods that every single object has, so we're allowed to call them even when we don't know the type of an object. Now, notably, it has to be an object. That's not true if they are primitives, and that's part of why type parameters cannot be primitives. We wouldn't be able to get away with this stuff if they could be primitives. But since they have to be objects, and every object has toString and equals, we got away with that. But we can't do much else. So with our next method, we want to find the minimum value of a linked list of doubles, which is going to need some less than operator, effectively. We are strictly actually going to use literally less than. We're going to need some less than operator, and that does not exist in all methods. We have equals, we have toString, we have a couple other methods that aren't useful in 116, like hashcode, and that's it. Like there's not much. There's not many of these methods that exist in every single object. Less than operator definitely is not one of them. And on your assignment, on your homework, you have to find a rating with a specific reviewer ID, which certainly does not exist in every object in Java. That's not core to the Java language that every object needs a reviewer ID. That would be terrible. It wouldn't make sense. So we have this situation absolutely on our homework. So let's do something to address this. We're going to find the min of a linked list of doubles. We're going to create a new class that's going to mirror the homework a little closer. We're going to have a linked list of doubles class, which is going to be a wrapper class which has a linked list of doubles as an instance variable, which I'll call numbers because I always call these numbers. Ooh, almost did a terrible thing there. So we have a linked list of node of doubles as an instance variable, which is going to mirror your homework, where this is going to be the song class, and you're going to have a linked list node of ratings as an instance variable in the song class. That's what you'll have on the homework. So this example is very much paralleling your homework and guiding you through how to set up your task 3 stuff. And when we initially create our linked list of doubles, we have this instance variable, which is a linked list of doubles, literally. And when it's empty, when we have an empty linked list, we set the variable itself to null. We don't do anything else. If I see anything else, if you do anything else than that, you're wrong. A lot of students like to, and I cannot for the life of me figure out why. I have my speculations, and none of it's good news for the student, is creating a new linked list and passing the constructor null and null, giving it 2 nulls. That is absolutely not anything I'll show you in lecture. It's nothing we do in 116. It's nothing anyone does out there on the planet. Like, nobody uses a linked list like that. I don't know where it comes from, but it comes from somewhere, and I see it every semester. It's one of the most common issues on task 3. Do not do that. An empty linked list, set the variable itself to null. That's it. Yeah, I don't need anything other than that. And then we need a way to actually add doubles to this thing. So let's do a public void add double. And this is going to be an append method, double to add. It's going to effectively be append. But we already wrote append in our linked list node class, and we don't want to redo work. Now as good a time as I need to mention this. Whenever I'm showing you code in lecture, or any code in this entire examples repo, it's all fair game to just cut and paste into your code for your homework. So we already covered the append method. I showed you exactly how to do it in method. I live coded it right in front of you. You can take this, copy it, go to your homework project, and paste it into your linked list node class, and just straight up use any code that we covered in lecture. So you can just use the append method. And then your add double, which is very much your add song method on task 3, is going to check. Well, first, the logic of this is going to be numbers dot append to add. Fundamentally, that's what we want to do. Oh, I forgot I made this. Fundamentally, that's what we want to do, but we have one big problem here, is if we run this, you know what, I'm actually not going to run this code, am I? No, I can't just not run it. Let's run it. So we're going to do linked list of doubles, linked list of doubles, list of doubles equals new linked list of doubles, list of doubles dot add double 5.6, list of doubles dot add double negative 1.2, list of doubles dot add double 1000.0. And then let's just print out list of doubles dot min. Just so this compiles, let's write our min method. Public double min return 0.0, just so our code compiles. And let's run this and see the issue that we're going to get if we just straight up call the append method, which is an issue we saw earlier in the lecture too. There's our big old null pointer exception. So the problem is that numbers is null initially, and then when we call add double, we're going to get to this dot numbers. This resolves to null, and this dot operator says take me to your object. There's no object to take you to when it's null. The null says, hey, we don't do that. Like what do you want? Where do you want me to send you? And it's just going to throw an exception and crash the program. So we need an extra null check here. We want to say if this dot numbers is null. So if the list is empty, then we want to set this dot numbers equal to a new. We want to create the list, the initial list, with to add, and next is null because we have a list of size 1. If numbers is not null, then we can just straight up call append. And this method's fine. This one works just great. So when you're on your homework and you're writing the add song method, it can look just like this. The add song method is given for free. This is what it should look like. And grab the append method. The append method isn't given in the homework handout code. I'm 99% sure. I don't think I added it. And so you can take the append code that we covered in lecture, and then your add song, it's this, except instead of double, it's rating. And it's whatever you named your instance variable. So that one's given. And then we want to write the main method, or the min method, to find the minimum value of all of our values. So first, again, our null check. When our empty list is represented with null, we have to be careful about null pointer exceptions because numbers can and will be null sometimes. So we always have to check if numbers is null, which is to say if the list is empty, if we have no numbers added to this list, then we want to return something. And I'm going to get a little cute with this and do double dot positive infinity. Something to indicate that something went wrong. In the slides, I returned -1 here, which doesn't really make sense and it kind of bugs me. But double dot positive infinity, the largest possible value that can be stored in a double. And else, we're going to make a recursive call because I want to use recursion. I want plenty of examples of recursion today. We want to make a recursive call to min. But what do we do here? So the way we advance our code, and this doesn't work, this is just infinite, but the way we advance our code when we have recursion is to pass new parameters. That's how we're advancing our code closer to the base case of our recursion. But that doesn't quite work here because we don't have any parameters. And we can't take advantage of the keyword this because this is a reference to a linked list of doubles, which has access to numbers, which is always going to be the head of the list. We don't have a mechanism to be able to advance through the list like we did in linked list node. We took advantage, like size didn't take any parameters, but we took advantage of the keyword this, which is a hidden parameter of every single method. We have the keyword this. But this time, this doesn't help us at all because it's a reference to a linked list of doubles, not a node. So we have no way of advancing to the next node. So when we're in a jam like this, we want to use recursion, but we don't have the parameters we want. What we'll do is write a helper method. We'll write a method, and I always just call these straight up helper methods, min helper, with the parameters that I want. So I want as a parameter, what I want to keep track of is the node that I'm currently visiting. So a linked list node of double, which I'm going to call node. So this is the node that I'm currently processing, where usually this was going to be this, now I have to create my own variable. I can't just use the keyword this. So whatever, I'll just create my own variable, make it a parameter of the recursion, an explicit parameter instead of the implicit this, and then use that to be able to go through my linked list. And I also want, just for this specific application, like our other methods the methods themselves had some parameters. I want a parameter that keeps track of the minimum value that I've found so far. And then I'm going to seed this. I'm going to start at the head node of the list and min as a value whenever you're doing min and max problems, making sure that min and max are not something that's going to interfere with your logic. And I think positive infinity is plenty large enough that it's not going to interfere with my logic. Whatever the first value of this list is, it will be smaller than positive infinity. That we can pretty well guarantee that. The worst that can happen is it's equal to, which still works for our logic. And integer, this is something like for best key. I should show this before best key. If you do integer.min value, it's the smallest value, the largest negative value that can be stored in an integer. So if you initialize at integer.min value, you're never going to interfere with the logic of your best key method. But for that method, I think my test case goes to like -10 at most. So as long as you're thinking about negative numbers, you'll be fine with that. If you initialize to 0, you got more work to do, and you submitted to AutoLab and realized you had to fix your issue. But as long as your initial value was like -100, you got away with it. But integer.min value would be the most proper way to do that. Okay, so now our recursion. So if node equals null. So this is a little bit different setup on the recursion too. Instead of saying if next is null, I had to do if next is null with linked list node because I can't make the recursive call on null. But here I'm going to do things a little different. I'm always going to make the recursive call, and I'm going to check, did I get null? Like, is this null? Actually, now that I look at it, I don't even need this. I'll leave it here, but I actually don't even need this condition because I would have null, positive infinity, and then it'd be returned as positive infinity. But if node is null, I'm going to return min, and I'm going to keep updating min as I go through the recursion. So by the time I get to the end of the list, min is going to be the minimum value of all of the nodes in the list, and I'm just going to return that as the answer. Else, I have more work to do. Node is not null, so there's some processing to do on this node at least. So I'm going to say if node.getValue, I have to use my getters now, getValue is less than min. That means I have a new minimum value, and I'm going to make the recursive call. I'm going to return min helper of node.getNext. So I'm going to advance to the next node and pass this node's value to it. If this node's value was not less than min, I'm going to do mostly the same thing, except this node's value is not the new minimum value, it's the old minimum value. I didn't find a new winning value, so the min is still the same as it used to be. So I'm still going to just pass min. And that's it. You only got to process one node when you write recursion. You handle your base case, you assume your recursive calls do what it's supposed to do, and you just handle one node. We just did one comparison. It's basically just the guts of what your loop used to be. And then the recursion handles the actual, like, going through every value. Our min value is -1.2. We get -1.2 printed to the screen. All right, let's talk about removing a node quickly, and then we got to move on to stacks and queues. So removing a node it's something I'm not going to show you what to do. It's the bulk of what you're expected to find out, to get practice with on your homework assignment. But removing a node, to remove a node from a list, oh, I didn't set a breakpoint. So we have this list, oops, with 5.6, -1.2, and 1,000. And if we want to remove a node, say we want to remove the node with the value -1.2, what we'll need to do is have a reference to the node 5.6 and then update its next to this node's next. So 5.6, its next, which is now a reference at 968, is going to have to be updated to the reference 971. So when we do that, this node, instead of having this one is a next, it'll skip this one and effectively cut that node out of the list, and the list will be just 5.6 and 1000. So to do that, we would do something like list of doubles dot, we're inside this class so we can actually access the instance variable directly. Numbers, which is a reference to the node 5 with the value 5.6, and we can set its next equal to list of doubles dot numbers dot get next, which is a reference to the node with the value -1.2, and we get its next, which is a reference to the node with the value 1000. So we're updating the head of the list to be its next node's next node. And if we rerun the debugger, now list of doubles is just those two values. We effectively cut -1.2 out of the list by manipulating our references by updating that next reference. And then this node with the value -1.2 will actually get garbage collected. We can no longer access it. We have no references to it. It's going to be gone. It's going to be deleted. So that's how we remove a node from a list. I said I wasn't going to show the code, and I kind of did. But I wanted to make it more clear because this is one thing where I think the slides really help to get the visuals. But the things to be careful of when removing a node is what happens when you're removing the last node of the list and what happens when you're removing the first node of the list. Removing the first node is a little special because your list is going to be an instance variable, and that instance variable needs to update. So if you're removing the first node of the list, numbers itself here would have to change to a reference to numbers.next, which is kind of what we just did in the main method. If it's in the middle of the list, it's next value. And if it's the last one of the list, the big one there is making sure that you're checking in the right order if that node needs to be deleted. If it is a rating to a reference to a rating with a reviewer ID that you're looking for, making sure you get this in the right order. If you do all those things, you should be good on that remove node method. Okay, moving along. Let's make a stack. So the stack data structure is your first in, last out data structure. That looks wrong, but first in, last out. So whatever the first thing added to the stack is the last thing you return. And you can think of this as a physical stack. The first thing you put on the stack, if you put something on top of that, you can't access this value anymore. You keep putting things on top of the stack. You can only remove from the top and then reveal the things that are underneath that thing as you're removing from the top. But you can only remove, you can add to the top, which we call push. Add a value to the top of the stack. And you can pop. Remove a value from the top of the stack. That's all you can do. Push and pop. That's a stack. That's your stack data structure. Some implementations of a stack give you more methods like peek and top, which let you look at the top value of the stack without removing it. But that's not strictly required for the concept of a stack, the theory of a stack. Push and pop, it's all you need. And pop will remove the value from the top of the stack and also return that value when we write it as a method. So it does double duty. And that's it. And whenever we do our memory diagrams and we have stack memory, that is effectively a stack of stack frames. It follows this first in, last out data structure. That philo, it just looks wrong to me. Do I have the wrong? It's not wrong, but is it? Yeah, last in, first out. In, first out. Just looked a little weird. It means the same exact thing, but I want to be consistent. Last in, first out. Is the same as first in, last out. But the last one in the last one you add to the top of the stack is the first one that's going to be removed from that stack. And stack memory is a stack of stack frames. So the last method call you make, that last stack frame, you can only add it to the top of the stack. And then once that stack frame returns, it's going to pop off of the stack, and whatever stack frame called it, the one next on the stack, that's the one that's going to be active again. In your main stack frame, you can never get back to that one except by removing all of the other stack frames to get back to main. You can only mess with the top of a stack. And very much so, a stack memory is a stack of stack frames. Now we draw our memory diagrams upside down, so the top of the stack is visually on the bottom of our memory diagrams in the tracing tool, but it is still conceptually the top of the stack. So that's the data structure we want here. And let's build this thing. So first, our stack is going to take a type parameter. I'll call it T again. And we're going to have, just like the linked list of doubles and just like your song class, we're going to have an instance variable that's going to be a linked list. So we're going to have a linked list node of T, which is going to be the top of the stack, which is going to be the head of the underlying linked list. And we're going to work just with the head of the linked list when we work with this stack. And I'm going to initialize that to, I'm going to do this a little different. I'm going to do it the same way I did in the slides and mix styles here. But I'm going to have a constructor, which is going to set top equal to null. Now, for those of you who are really observant, you know that top actually does get initialized to null even without making it explicit. But I like being explicit here. And also with the linked list of doubles, I didn't add a constructor, so I used the default constructor, which doesn't do anything and takes no parameters, and initialized it inline. Both of these have the same exact effect. I'm initializing my value to null. Even if I completely erase this, this still has the same exact effect. But I just want to be explicit, so when you're looking at the example, you know exactly what's happening. Top is initially null, is a good reminder. And then we have two methods. We want public push, which takes a value, returns void, first of all, and takes a value of type T. And we want public pop, which doesn't take any parameters and returns a value of type T. So let's get push. Push is actually exactly like prepend. This is exactly prepending, which we did as our very first thing for a linked list. The first list that we created is we're replacing a variable that stores a linked list node with a new value that refers to the old head of that list. So we're going to say this, except we're writing it as a method this time. This.top equals new linked list node of the value we're adding, the value we're pushing, and this.top. So same exact logic we did before, it's just in a method and with an instance variable, so a little combining things that we know here, but we're prepending to this list. And we actually don't even need a null check here. When we're prepending the first value, we're creating a new node, and if this.top is null at the moment, great, it's null. That's what we would have done anyway. So we have a linked list of size 1, some value, and null. That's great. And if top isn't null, we're still just prepending to the list. So that's our whole push method. That's all we need. It's just pushes exactly prepend. Pop, we do have to do a little bit more. We do need our null check. So if this.top is null, we're trying to pop off an empty stack. In most implementations of a stack, this will throw an exception, and it'll either crash your program or you got to catch it. We haven't talked about that yet. But you get a pop off an empty stack exception. Instead, just to keep things simple, we're going to return null if you try to pop off an empty stack. Else, we actually have to do the pop, and we want to return this.top.value, .get value, because we're not in the linked list node class anymore. That's kind of what we want to do, but we can't really do that because we also want to remove that node. We know top isn't null, so we know we can use the dot operator on top. So this dot top dot, this dot top equals this dot top dot get next. So we're effectively removing the top node of this stack. But if we get its value after we remove it, we're actually getting the second value, and we just lost the top value of the stack. So we can't quite do this. We kind of have a circular dependency issue. Like, which one of these do we do first? We can't return and then remove. Just gets wonky. So what we need is a temp variable. We're going to get the value at this node and store it in some temporary variable. Then remove the node, and then we can return that value that we stored. So it's a classic case where we need some temporary variable to be able to get the whole job done. Then in our main method, we're going to have some stack. I'm just going to do integers, keep it simple with integers, a stack of integer syntax. Stack of integers, stack equals new stack. Stack dot push 5 5 1 negative 7. Did I used negative 7 or 8? Negative 16. Int x equals stack dot pop. Let's take a look at what happens in the execution of this code. I didn't print anything to the screen, so no reason running it, but let's just run the debugger and see exactly what happens. So we're creating a new stack. Top equals null, but top was already null. We're just replacing null with null. It is what actually happens, but I like being explicit. So we have our stack object where top is null. We have an empty stack. We're going to push 5. So top is assigned a new linked list node with the value 5 in this dot top, which is currently null. So after that executes, we get a linked list node constructor. After that executes, top is now a reference to a linked list node with the value 5 and a next of null. We're going to do the same thing. I'm going to skip over the next 2 pushes, and top is now negative 16, next is 1, and next is 5, and then a null. So that's our whole stack, negative 16, 1, and 5. And when we pop, we're always going to pop the top of the stack, which is 16 here. So when we pop, we expect 16 to be returned. Top is not null. So we're going to grab negative 16. We're going to update top to remove negative 16 from the stack, and I'll jump over this one. We're going to remove negative 16 from the stack, so now the stack is 1, then 5. And then we're going to return negative 16, which we're storing in that temp variable, which we no longer have access to. If we didn't do the temp variable, we can't access negative 16 anymore. So we did need a temp variable there. And then x is going to have that value negative 16, and the stack is now 1, 5. If we pop again, we pop 1, pop again, we pop 5, pop again, we get null. Okay, and that's stack. We actually got through that pretty quick. So stack, the reason we would use stack or a queue that we're about to see is I was worried about writing all that code and losing a bunch of time. But it looks like we might finish queue right on time. So the reason we would use stack and queue, because this is a limited data structure, we only have 2 operations. The reason to use these is because these 2 operations are extremely fast. Nowhere in push or pop do we care about how big the stack is. It does not depend on the size of the stack. They just do their thing and that's it. We don't have to traverse the entire stack, the entire underlying linked list. We don't have to do any of that. Let me get it right here we just do our thing. These are called constant time methods, constant runtime, or O of 1 time methods, because they don't care how many values are in the data structure, as opposed to O of n methods. So like asking a linked list for its size has to traverse every node in the linked list. So we call it O of n or linear, meaning that it depends linearly on the size of the list, where the size of the list is n. These methods are O of 1. They don't care how big the list is. Pushing and popping always takes just constant amount of time. So again, I did mention this, didn't I? In 250, you'll really, no I didn't. 250 I was talking about I was still talking about the comparison of array list and linked list. So stack and queue, one of the big trade-offs here is efficiency. These methods are extremely efficient, even though you do lose a lot of functionality. Like notice you can't ask a stack for its size. Something you might want to do. You might want to do that pretty often. You can't ask a stack for its size. But that's the trade-off. You lose functionality, but you get only efficient methods. So let's do the same thing with a queue. Queue is our first in, first out data structure. It's just like queuing up for any line you've ever been in. You enter the queue at the back, and then once you get to the front, then you get to exit the queue. And the first person to get in the queue, they're the first person to get out of the queue. You get up in line, first one in line, you're going to be the first one out of that line. First in, first out. And this has two methods, in queue. In queue, which is append to the end of the queue. And dequeue, remove from front of the queue. So these are our two methods, just like push and pop. The trouble here is that we are working on both ends of the queue. So we can't use our linked list exactly the way we have been. We need our type parameter. I'm going to still use t. Linked list node of t. So we can't exactly do this the way we've been doing it before, but I am going to have the front. I'll set it equal to null like this. Well, so I'll do it backwards from the stack. The stack, I had a constructor to make that explicit. Here I'm going to do it explicit inline, just like I did with linked list of doubles, just to emphasize that both of them do the same thing. We're initializing these things to null, and even if I don't do anything, they're still initialized to null. Ow! They're still initialized to null. So since I have to work on both ends of the list, I want to, I need to be careful about the way I write in queue, because we have to append to the end of the list, but append is an O of n operation. It's going to take O of n time to ask each node, hey, where's your next node? Where's your next node? Where's your next node? Where's your next node? Traverse the whole list to get to the end to be able to append. That's slow, and that's not allowed. These need to be O of 1 operations for stacks and queues. So I have to do something a little more clever. And what I'm going to do is track a second reference, which is going to be the back of the queue. So I'm going to have one linked list, but I'm going to store two references to two different locations in that linked list. And then I'm ready to write in queue and dequeue. So void enqueue, some value, and public t dequeue with no parameters. So enqueue is going to append to the end, and what I'm going to do is, one, I need a null check here. Ooh. So if front equal null, so if front is null, back should also be null. If this queue is empty, front and back need to both be null. So I'm just going to check one of them for null, and the other one better be null, or else I have a bug in my code. So if front is null, then this dot front is going to equal a new linked list node. So if the queue is empty, we just got to get this value in as the only node in the queue. So we're going to create a linked list of size 1. But importantly, if we have a linked list of size 1, a queue of size 1, front and back need to refer to the same object, the same node that we just created, because these are two references to the same linked list, just different locations in the same list. So if the list is empty, we create one node, and front and back are both that node, because they're both the first and the last person in that queue. Else, the queue is not empty, and then we're going to append to the back. So this dot back dot set next to a new linked list node of value next, So we're appending to the end, which we can do in constant time. Sorry, null. Which we can do in constant time because we have a reference to the back of the list. We're already at the back, so we can immediately append because back.next is going to be null at this point, as long as we don't have any bugs in our code. And then we have to update this.back equals this.back.next to make sure that we don't have any bugs in our code, get next. We have to advance back to make sure it's referring to the end of the queue still after that happens. And then DQ, I'm going to cheat a little bit here. I'm going to grab pop because it's basically the same thing. We're removing from the front of the queue. It's exactly the same as removing from the top of a stack. Oops. We're just going to replace top with front. But there's one extra thing that we have to do. Is after we DQ the node, after we remove it from the front of the list, if that was the last node, so if this.front is now null, we have to make sure our references are lined up that back is also null. So this.back we need to assign to null. Because if we remove the last node from the queue, then front is going to be null, but back will still be referring to that last node that we removed. So we want to make sure we update back's reference to also be null to make sure we're back in this null position that we started in, to make sure that here, if we're just doing a check for front, back should also be null. We need to make sure that assumption is still true after we've enqueued and dequeued a whole bunch of stuff. And with that, let's do exactly that. Let's enqueue and dequeue a whole bunch of stuff. So by having two references here, we were able to get these both to O(1) operations still. So we had to do a little bit more work to get the queue to work with a linked list, but we did get there. So let's create our queue of integer queue equals new queue queue.enqueue 18 seems fine. Enqueue -59, sure, and 104. Int x equals, let's dequeue a few times, queue.dequeue. Let's dequeue from an empty queue as well. So let's go through this. We have our empty queue, nothing too interesting there. We're going to have a queue with front and back both equal to null. Then we're going to enqueue 18. We're going to see that front is null. So we're going to set front equal to a new linked list node. So front, this.front is assigned to some node. But we have back equal to null still. So back is saying, hey, we're an empty list. We're an empty queue. But front is saying, no, we have the value 18. So we have to make sure they're in sync. We're going to assign back to front as an assignment by reference. So back and front are both referring to the same object, this linked list node at 942. So they both are referring to the node with the value 18 and a next of null. And the queue effectively has a size of 1. We're going to enqueue 59. Now front is not null. So now we don't have to mess with front at all. 18 is the front of the queue, and until we dequeue, that will remain true. And so we only have to mess with the back of the queue. We're enqueuing at the back. We're done messing with the front until the queue's empty again. So we're going to update back to have a new node. I'm going to skip over all the details of the constructor and set next, but back is next, which was null, is now going to be a new node with -59 and null. And then we have to update back, because back is no longer a reference to the last node in the queue. So we have to update back to be, oops, I'm in get node. We have to update back to be the last node in the queue. And notice front and back were referring to the same object. We updated back. We changed its next value and then updated the reference. So front also sees that change. Front which is still a reference to the node with 18, but that node just got a new next added to it, this negative 59. Front sees that change. Back is a reference to the last node, but front is still a reference to the front node, but they are two references to different nodes in the same list. Same happens after 104. Back is a reference to the node 104 and next is null, and front is a reference to the node with 18 with a node with negative 59, next of 104, and then null. And this 104 node, 1109, needs to be the same reference as back, 1109. They have the same list. They're referring to the same list, just different locations in that list. At a glance, you might want to think that there are two linked lists in memory here. It's not true. There are one list, but two references to two different nodes in that list. Then we dequeue. Front is not null, so we're going to grab the value. And this works the same way as stack did. Grab the value, update front. Front is not null, so we don't have to update back as well. We're going to remove 18. So the queue, the front is now negative 59. Next is 104, and back is still a reference to 104. And we're out of time. I gotta call it there. We're a minute over actually. But this code actually does crash because when we return null, we're returning null into a primitive was the last point that I wanted to make. Turning null into a primitive will crash the program. Kind of just oh, it is a null pointer exception when that happens. I thought it was a different type of exception. But the value of a primitive can't be null. Null is the lack of a reference. Primitives don't store references, they store values. So you do get an error in that one. That one won't come up in your homework, but it's just a neat thing I wanted to show you. Whew, all right, that's another lecture down. And we are officially 50% done with lectures. As much lecturing as I just did this semester, it's halfway. I'm going to do that much again. Actually, a little less because the midterm day is only 1 hour of lecturing. But yeah, we're halfway done with content. Let that sink in. Summer moves fast. All right, I'm going to take a half hour, and then if I see y'all in office hours, I'll see you then. If not, I'll see you on Thursday when we're talking about inheritance. Take care, everybody.